Hi guys, so in this video we're going to be talking about recursion. So this is a very interesting topic and something to ponder upon, so don't take it lightly. This is going to be fun. So I'm going to start this video by with a story. So a guy called Peter is walking on the streets and he's suddenly seeing stick no bills on the wall, and he thinks to himself, isn't this a bill by itself? So what he does is, he's so jobless and dumb, so the next day he comes with another poster which says stick no bills. You get it? So he's basically saying, don't stick no bills. So, and the next day he walks again and he's like, isn't this a bill? And the next day he comes and with one more bill he comes which says stick no bills. You understand? So this goes on and on and on, like infinitely. So he never gets a job. So sad. So let's analyze this statement first. So this stick no bills is the outermost stick no bills, and then this stick no bills is the second outermost. This is the innermost, right? So now we can see that it goes inside with stick no and comes outside with bills. Yeah. So this is how recursion works. And one more thing you have to notice is that this goes on infinitely. Why does it go on infinitely? Because we never get to a point where we say that, okay, this is not a bill, so this can be there. Because how much ever we extend this thing, it will still be a bill. There is no condition which says that this is not a bill to terminate the process. It goes forever and ever. And that condition which terminates the process is what I call a cornerstone. This kind of like the vision in AI and all. It's because okay, so let's say we create a robot and we give it a memory, okay. So let's say I create a robot at the and I want to give it the maturity of a 25-year-old guy. So it needs to have some memories and stuff like that. But sometimes even we humans get the question, who am I, right? So when we think about who am I, we go back and back in a memory, we go back, and then at one point we stop and we say, okay, that's who I am, yeah? But for robots, we have to define even that manually. So the vision is basically you have to give some tragic event or some big event to the robot, so it terminates at that point. So when it thinks who am I, it goes back and back in its memory, and when that tragic event comes, it says, oh, that's who I am, that's how I came here. You understand? So that's the need of cornerstone, or this will get stuck in an infinite loop, and this will cover the whole universe. So yeah. So now I'm going to explain two functions. One is Factorial, which is the simplest recursion program ever to understand recursion, and then second one is Fibonacci, which has an interesting consequence. So let's see. Yeah, so this is a function for finding the factorial of a number n recursively. So let's see how this works. This works somewhat like this. So let's see how. So let's say in one function I'm initiating the whole recursion by calling fact of 5. This will basically return the factorial of 5, which is 120. So let's see how it does that. So at the first call, n is 5, right? It comes inside, it will check whether it's 0 or 1. It's not 0, neither 1. So it's gonna return n into, therefore 5 into factorial of n minus 1, factorial of 4. I guess you can see where this is going by now. Okay, so now, so I'm putting an arrow from factorial of 4 because this is a function call. So from factorial of 4, now n is 4, it will check whether it's 0 or 1. It's neither. So it will come down and return 4 into factorial of 3. Yeah? Now it will come down again. I will come inside again. Now n is 3, it's neither 1 nor 0. So now it will return 3 into factorial of 2. Oops, okay. And the same thing is going to happen again. So 2 into factorial of 1, and this factorial of 1 function is going to return 1. Okay, I hope you can see that. Okay, so this is 1 basically. Okay, now this factorial of 1 function is returning 1, right? So this factorial of 1 will be replaced by 1. Yeah, now this factorial of 2 function is returning 2 into 1, right? So this will be replaced by 2 into 1. You can still see where it's going, right? 2 into 1. Now this factorial of 3 function returns 3 into 2 into 1. So this will be replaced by 3 into 2 into 1. And factorial of 4 function returns this whole thing, and this will return 4 into 3 into 2 into 1. Now this factorial of 5 returns this whole thing, which you can clearly see there is a factorial of 5. This will multiply up to 120. So how is this and this similar? So when this function call goes in and goes in and goes in, it's like stick no and stick no and stick no. And when the return happens, it's like bills and bills and bills. And this bills is the total answer we're getting at the end of the whole recursion. So this is how a factorial function works, and this is what we call as a single recursion, because there's only one recursion call inside the function. In the next section of the video, we're going to take it a notch up and see how 2 recursions work and the interesting consequence it has. So this is the code for finding the nth Fibonacci number. For those who don't know what a Fibonacci series is, the series starts with 2 numbers 0 and 1, and from that we build up the series. So the third number is the sum of the first 2 numbers, so 0 plus 1, 1. The fourth number is the sum of these 2 numbers, which is 2, and then these 2, 3, and then 5, it goes on like that. Okay, so what this function does is, it basically returns the nth Fibonacci number. This is the first Fibonacci number, second Fibonacci number, third, fourth, fifth, sixth. Okay, so let's say I call fib of 5. Okay, so what this fib of 5 does, we'll see. So first we'll go in, n will be equal to 5, right? We'll check whether it's 1. It's not 1, it's not 2. So now we'll go to the return statement. So it will return fib of n minus 1, which is fib of 4. Yeah, okay. Now here n is equal to 4. It will check whether it's 1, no, 2, no. Now it will again come here, it will see, it's okay, it will call fib of 3. Okay, it will go again, it's not 1 or 2, so it will again, wait a second, and it's 3, so now we will call fib of 2. So when fib of 2 is called, it's 2, so it will return 1, so this will return 1. So this fib of 2 call returns 1, so this will be replaced with 1 now. This will be replaced with 1, so this part is done for n is equal to 3, so this part will be executed now. So plus fib of n minus 2, which is 1. Now think about this. Now n is 1, so it will return 0. So this fib of 1 will be replaced by 0. Okay. Now this n of 3 returns 1 plus 0. So this fib of 3 will be replaced by 1 plus 0. Now in n is equal to 4, this part is done. Now this part will be executed. So plus fib of n minus 2, which is fib of 2. So what is fib of 2? You check whether it's 2. Yes, it is. So we'll return 1. So this fib of 2 will be replaced by 1. Cool. So, okay. Now this fib of 4 returns is 1 plus 0 plus 1. So this whole fib of 4 will be replaced by this value, which is 1 plus 0 plus 1. Done. Now in fib of 5, which is the original call, this part is over. Now this part will start executing. So plus fib of 3. Yeah. Now now in this call, in this section, n equals 3. Here it will check whether it's 1 or 2. Now it's fib of 2. Okay, it's coming left. Okay, so now it's 2, so this will be, so this fib of 2 will return 1, so this fib of 2 will be replaced by 1, and now this part will be executed. So fib of 1, which is 0, so this part will be replaced by 0. Cool. So now this fib of 3 as a whole will be replaced by 1 plus 0. Now this is like the total bill, because we went inside with stick no, and we're coming outside like bills, and this final bill, the outermost bill, is the answer for this function, right? Because think about this stick no corresponds to this bill, this stick no corresponds to this bill, and this corresponds to this. So when we call the function, the outermost returning value corresponds to the main function call, right? That's pretty obvious. So compute this. 1 plus 0 plus 1 is 2, plus 1 is 3. 1, 2, 3, 4, 5. We're done. So this is how a double recursion works. Now let's see the pretty interesting consequence of double recursion. Okay, so now this structure is what we call a tree. This is a tree, like, and especially this tree is called a binary tree, because every number, like, okay, every section has at most two branches, right? So this is a binary tree. So we can use this structure as a data structure, and we can use it a lot. Like, you will come across a data structure called tree which has very similar structure, and through the whole concept, in every single function you will see recursive functions, because double recursive function, more than 2 recursive function itself, will act like a tree. Like, let's say there are triple recursive functions, then it will act like this, and then from here there'll be 3. Yeah, so only when there is only one recursive function, it'll act linearly, otherwise it'll act like a tree. So this is why trees are very useful, because we can accomplish a lot with recursive function. Even now you would have realized the power of recursive function. And yeah, and one more thing is that now what we're basically doing is, we are traversing through the tree, right? So this way of traversal we are doing now is called in-order traversal. So what we basically do is, you start from the uppermost element and you go left until you hit the end, until you have no more left elements, and then you come one step back, you take right. You again take left until you hit nothing, and then you come back, you take right. So if you keep doing the same thing till you literally there's no more actions to do, you would have constructed the whole tree. So we'll see that in later lectures. Thank you.